everyone. So we're going to start with one more example using the epsilon delta definition of limits to prove a limit. Then we'll present the laws that will make finding limits like that a lot easier. And then we'll end with the highlight of this section, which is the squeeze theorem. So let's prove that the limit as x approaches 3 of x squared equals 9. So again, first we guess a good value for delta, and then we prove that that delta works. Okay, so we have that f of x equals x squared, L equals 9, and A equals 3. So given an epsilon greater than 0, we need to find a delta greater than 0 such that x squared minus 9, that's f squared minus L, is less than epsilon whenever 0 is less than x minus 3 is less than delta. So that's the A. So what we have to do is somehow force x squared minus 9 is less than epsilon into terms of x minus 3 is less than delta. And then use the fact that x minus 3 is less than delta to prove that if this is true, then this has to be true too. So we have to connect x squared minus 9 with x minus 3. Well, we can do that by factoring x squared minus 9. So x squared minus 9 is the difference of two squares. So we have that x plus 3 a rule of absolute values is that the absolute value of AB equals the absolute value of A, the absolute value of B. Okay, so we know that x minus 3 is less than delta. We have to find a way to control x plus 3 to keep this whole thing less than epsilon, and then connect the epsilon and the delta. So we can find a positive constant c such that x plus 3 is less than this constant. So we can find some constant that will be larger than x plus 3. Then we'll have that x plus 3 times x minus 3 is less than c times x minus 3, right? Because the c is greater than the x plus 3. So what we're doing here is kind of like circling in on some kind of a guess, because we don't know what c is, and we don't know yet what delta is. We don't know what x plus 3 is. But we do know that we can find something that will be bigger than this. So let's keep looking at whether we can find some more information about that. So what we need to do is to make sure that c times x minus 3 is less than epsilon. And remember, what we're looking for is to pick delta. Well, if we want to keep this less than epsilon, and we know that x minus 3 is less than delta, if we divide through by c, then we'll have that x minus 3 is less than epsilon over c. And we can set that equal to delta. So now we know that if delta equals epsilon divided by c, then c times x minus 3 will be less than epsilon. And we picked c so that c times x minus 3 is larger than x plus 3 minus x times x minus 3. So this will work to show that x squared minus 9 is less than epsilon. So maybe this is a good start. We've at least sort of done the problem here, but we don't really know anything about c. This is completely arbitrary. We're just saying that we can pick any c that's going to be bigger than x plus 3. Well, yeah, but we haven't really accomplished anything yet, because we need to come up with a rule where you give me the epsilon and then I can just spit out a delta without thinking about it, just automatically. This epsilon creates this delta and show that it'll always work. So we're starting here, but we haven't really finished it yet, because this doesn't really tell us what we're going to have delta be for any given epsilon. So we know that we're interested in values of x that are, close to 3. How's that for a graph? So we want values of x. I should draw it this way. Say this is our function, and here's 3, and we want x that's going to be close here so that f of x will be in here somewhere. And this is L. So we know that the important detail is when our interval around 3 gets closer and closer to 3. It doesn't really matter as epsilon gets bigger because then the interval around the 3 can also get bigger. But it's important to notice that if a bigger interval works, then a smaller interval will also work. So it would be reasonable to say that we're just going to restrict what we're looking at to an interval of 1 on either side of 3. So that is the distance from x to 3 is less than 1. And then we can rewrite that. That means that minus 1 is less than x minus 3 is less than 1. Then we move the 3 over to both sides. And we have 2 is less than x is less than 4. So the important thing to understand is what I'm saying here is we're not saying that a delta of 1 is good enough to solve the problem. But we're saying that we never need a delta that's worse than that. I just want to say this one more time because I think this is the hardest part of this proof to get your head around. I'm just arbitrarily picking a 1, and it's completely out of the blue. And the reason that's okay is because no matter how big the interval is, even if we said that the interval between 1 and 100 worked for the epsilon that you chose, if that was true, well, then the interval from 2 to 4 is also going to work because this is a subset of this. So any interval bigger than this includes the interval 2 to 4, so we can always just say it's 2 to 4. If it's anything bigger, we're just going to look at that part. Okay? So we've sort of restricted, we're just kind of putting a stake in the ground about x minus 3, that it's never going to be bigger than, the distance is never going to be bigger than 1. But what about the x plus 3? Well, now using this, if we just add 3 all the way through, then we have that 5 is less than x plus 3 is less than 7. And that means we can rewrite this to say that x plus 3 is less than 7. So that means that we can choose 7 to be our C. Okay, so we're just picking this 7 from our restriction of delta to 1 and minus 1 around 3. So if that's the case, then that means that x plus 3 is never going to be bigger than 7 because we're restricting x to be no bigger than 4. So c equals 7 can be our upper limit for x plus 3. So this is good, but this is only the upper restriction. We don't yet know what happens if you choose an epsilon that's very small. Then we're going to need a delta that's a lot smaller. So we have an upper limit, but we still need to find a lower limit. So with this in mind, we now have 2 restrictions on x minus 3. First, we know that x minus 3 is less than 1. That's just because we chose. We're not going to look at anything bigger than that. And second, we figured out above on the last page that since x plus 3 is less than 7, then x plus 3 times x minus 3 is less than c times x minus 3. So we have 2 restrictions on x minus 3 now. We have that x minus 3 is less than 1, and we have that x minus 3 is less than epsilon divided by 7. So if both of these restrictions are satisfied, then that should work for any epsilon. So we want our delta to be such that these 2 inequalities are satisfied. The notation is that min 1 comma epsilon divided by 7. So whichever one's smaller, if epsilon is big, then we'll just pick delta to be 1. That's good enough. If epsilon is smaller, then we'll pick epsilon divided by 7, and then that should still keep the equation less than epsilon. So this should do it. Given any epsilon, no matter how small, this rule should give us a delta such that f of x minus L is less than epsilon. Okay, so now we have to prove it. Okay, so we're given that epsilon is greater than 0. Let delta equal min. So if x minus 3 is less than delta, then first x minus 3 is less than 1. The reason is when we're dealing with minimum, it's kind of weird because what you actually look at is the bigger one. If delta is the minimum of one of these, it's always going to be less than both of them. So in every case, x minus 3 is going to be less than 1, okay? That implies then from what we did before, that 2 is less than x is less than 4, and therefore, if we add 3 through here, we have that, x plus 3 is less than 7. Now, we also have that x minus 3 is less than epsilon over 7. And it's for the same reason. No matter which one of these is less than, the delta is going to be over here. So in either case, x minus 3 is going to be less than both of them. So given this, we have that whenever x minus 3 is less than delta, then we have x squared minus 9 equals x plus 3 times x minus 3. So now this is less than 7 times epsilon over 7. Cancel the 7s, and that equals epsilon. So we just showed what we needed to show, that whenever x minus 3 is less than delta, then x squared minus 9 is less than epsilon. So that's what we needed to show. So we've shown that the limit as x approaches 3 of x squared equals 9. So this example shows that it's actually not always easy to prove a limit using epsilon delta. And if we had something more complicated, like 6x squared minus 8x plus 9 over 2x squared minus 1, for instance, it would be very difficult to figure out how we would manipulate this in order to get it back to something that's in terms of delta. So fortunately, it's not necessary to prove each limit directly using epsilon delta, because we can use epsilon and delta to prove several limit laws, which will then allow us to dramatically simplify these expressions generally. So that's what we're going to look at now.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.